Quite the delay. So, hello. And I've just realized that there is a bit of a delay on this live stream. So, the setup you just saw. Hey, well, I can edit that out. Good morning, good evening, wherever you are. You just did your first GCSE exam. So now you've got a little bit of an idea about what to do next, because you probably had a lot of regret and reflection and probably a lot of glory too. And things that came up that you're so glad that you practiced. Today we're going to be looking at probability. Definitely one of those ones for a calculator exam. Very rarely do they come in the non-calculator, so it's a good time to do it. There are 16 days left until exam 2. From now on, it's calculators all the way. And make sure that you're comfortable with your calculator. Like right now, go get it. Because if you're not, borrowing one is going to throw you off your game, for sure. Today, it's expectations, tree diagrams, conditional probability, and Venn diagrams. Okay, let's get started. Oh, quick reminder, if you do want these questions, go to Patreon. They're all there for you. And have a go. Okay, questions. Raphael is moved to buy 15 online tickets at £3.50 each for a charity raffle. When the buying process is over, he is informed his chances of winning is 0.022. How much money was raised for charity? Assume that the prizes were donated and organizers work voluntarily. So that gets rid of our assumptions about hidden costs and, how much it's going to be won, because we'll have to take some out. How do we tackle this one? Well, if we know how a raffle works, each ticket goes towards a chance of winning. So if we know that 15 tickets were purchased, let me just get the pen going. We know that 15 tickets were purchased from Raphael. Don't worry about the fact that they're £3.50. When the buying process is over, he's informed his chance of winning is 0.02. So there's some amount, and I don't know how to write this for you, but let's say 15 out of some amount, that's how probability works, is equal to 0.022. So there's a total we don't know. But if we did the division, we'd have this. You see, this is an equation. So let's do the old switcheroo. We saw this from a different live stream. These two elements, if you have this setup of an equation, those two elements can just switch. So this unknown total, 15 divided by 0.022, is 681.8181. Now when it comes to it, why do we have 0.81? So we talk about how many tickets were sold, and 15 of them represent this. And sometimes statistics are presented inaccurate and rounded. So we can make some assumptions here ourselves. So in this case, the total, if it's 681.81, is there any clue to tell us which way we go? If it's rounded, then it's likely to have been smaller. And if that was smaller, it would have gone into it more. So I'm going to round it up. 682. So let's say that so far, this is going to be an estimation by the looks of it. so far we're at a point where we have the amount of people. And if this is the amount of people that have bought tickets, there were £3.50 each. A country can grow on one. And I keep saying dollars. Then we're going to multiply that. £3.50. And there's not much else in the way of fees. But this would be an estimated amount of how much this raffle has, charity raffle has raised, because everything else is voluntary and there's no other money to go out for prizes. It's not a bad effort, is it? Not bad. But this is using probability basics, I suppose. The number on top is the number of interested cases, and the number on the bottom is the total. And it could be written as such. And it's kind of good to explore here. If we had one ticket out of the 680, let's be accurate, it was 682. Then we're going to have a much lower probability of winning. If we owned all of them, we owned 682 out of 682, then our chance of winning would be 1. So 1 represents certain, like it's definitely going to happen. And if you have less, like the smaller the probability, whatever that is, it's less certain. It's uncertain. And that's how we put them on a scale, on a spectrum of probability. Okay, in a friendly football team, there are 20 players training each week. 11 of the players are on the main team, and 9 are regular subs. A player is picked at random. Let me see if I can zoom out here because it's pretty intense. That's better. A player is picked at random to be captain for Team A, because that's event number 1. It's kind of good sometimes to get recognizing events, and a player is picked at random. That's the first event. And then a second is randomly chosen for Team B. That's event number 2. So when you do enough of these questions, you start to pick out these things early, before you even know what the question is. Nothing else to say there, I suppose, except this is 11. Some people like to write it. I'm one of them. If I see it in words, it's less obvious. And we draw a tree diagram to represent the information. So there are 20 players. That's another good thing to have, because that's our total. And a tree diagram. So tree diagrams are in a specific format. Let's just say there were 2 events, and so each of these represent the 2 events. Okay, so that's the overall structure. We've got those 2 sections. The first section is the event when the first player is being picked at random to be captain for Team A. And really the focus here is the fact that there are 2 different groups here. They could be regular, or they could be, we should call them subs and main, so M and S. So there are 2 options on the first event. That player could be from the main team, or they could be from the regular subs. And it's still true that because there's more than one of each of those, it's still true that the second time we pick, we could have another main player or another sub. So here's our tree diagram, starting off with a nice simple 2x2 tree diagram. And there's not enough to get us our full marks. We need to write in the probabilities. In the first instance, there's going to be 11 on the main team out of a total 20. So that's the probability that they would be picked. And 9 out of 20. So again, we're talking about this as the first event. The probabilities in that first event have to add up to 1. And you can see they do. 9 20ths and 11 20ths. That's 20 20ths, which is 1. Now look at the second event. This time, it's a bit conditional based on what's just happened. Because if we have one person already picked, then that's going to affect the probability of the next person. So in the instance that it was the main player picked, there's one less main player and one less overall player to be picking from. That's immediately going to get you a mark because you've identified the necessity of the 20 denominator turning into 19. So be sure to note whether it's conditional probability or not. That's with one event affects another, and this one it does. So all of them, all of the denominators on the second half are going to be 19. That's a given. We can put that in straight away. But since the first player in the top was from the main, there's still the same amount of subs as there was when we was picking fresh. So that remains 9. Down the bottom, if the first one was a sub, then that remains 11 on the second pick for the main players, and then there's one less. If that first one was a sub, then the chances of a second one, there's only 8 left in the room that are subs, and therefore it's down to 8. And when I do tree diagrams, I tell you always write the outcomes at the end of the tree diagram. Now, I'm pretty sure everyone's enjoying their first weekend after hitting the exams. If you're joining after, take your time, do it when you can. I'm just going to do this as thoroughly as I can. Sometimes it's good to listen to me on ×2 speed. Other times you want to take it in properly. Okay, so MM. I've also got this really weird, well, it's not weird, it's a good habit I think, but it's sometimes not the best if the diagram is very big, but this is not a very big diagram. Sometimes we don't need all of these answers, but here it's not too onerous to do it, so I'm going to calculate all of the eventualities to begin with. And it's a good habit to get into. It's like becomes automatic. We'll notice in all of these cases that 20 times 19 is on the bottom. And because we might add these together, it's advantageous to keep the same denominator. So I'm going to go ahead and write that now. Okay, so we've got some repetition on the denominator, but not on the top. So first, 11 times 10, 9 times 11, 11 times 9, sorry, and then 9 times 8, 72. Now we should find that 110 plus 99 plus 99 plus 72 equals 380. I could tell you it does. So there's another rule. This is one event and it must add up to 1. This is another event, it must add up to 1. Here's another event, it must add up to 1. And lastly, the overall scenario is an event in itself. All these eventualities must add up to 1. So what we're saying is the chances of it being either one of them is certain. More importantly, which one? So this extra stuff that I did past here, that's not going to be needed for this, but it's pretty inevitable that it comes up at some point, so it's a good habit. Now, what is the probability that these two captains are not on the main team? What does that mean? If they're not on the main team, that means that they must be both on the subs bench, which means we're looking for one particular scenario. Oh well, we did all these, but it's fine. The probability that they are not on the main team is essentially finding the probability of SS, which we've already found is 72 over 380. It's possible that you are asked to simplify this, and they're both even, so you can. That's going to go down to 18 over 95. But it's not always essential, and that's how we do a basic tree diagram. And in fact, it's not so basic, is it? It's conditional. And with conditional, you need to be very careful with that denominator, but that's just the way it is. I find that that's pretty nice. Maybe I've practiced enough, so that would be my tip. Practice plenty of these. Okay, a dice is thrown 3 times. Gosh, sometimes I don't remember writing these questions. I like seeing them fresh. A dice is thrown 3 times. Okay, so a dice has 6 outcomes. What is the probability of getting at least 1 6? Interesting. So imagine all those possibilities. I mean, we can think it through. If it's thrown 3 times, then it could be 1 1 1, 1 1 2, 1 2 1, 2 1 1. So I've introduced, like, the first one where there's 3 1s, but then it could be 1 1 1, 1 1 3. In fact, let's not do that. Let's do 1 1 3, 1 3 1 3 1 1. It could be 1 1 4. You get the idea. And then once you've done 1 1 5, 1 1 6, and then you've got all of them in their different locations, like so. You then are introducing another number. So instead of 1 1 2, call it 1 2 2. 1, and keeping that constant now at the end. 1 3 2, 1 4 2, 1 5. All right, this list goes on and on, and it's to write out all the different possibilities. It's pretty crazy. You've got 6 in each position and 3 different positions. So we're going to think about it a little bit more carefully, I think, and rather than exhaust everything, we'll try and find a clever way of doing it. So if we talk about getting at least 1 6, there's a lot of scenarios. So that would be, a 6. Well, if there's at least 1 6, it means it includes 1 6. So we could call about 6 1 1 6 2. In fact, we'll do it in order. 6 1 3 6 1 4 6 1 5. And these are all the different ones, for example, with 6 at the end, but we could have 6 in the middle. Or 6 at the front, like so. So it gets to be quite a tricky one. So how do we do it without going through all of those different possibilities? Have a think. I just need a drink. Well, we think about it in terms of boxes, I suppose, or some people call them bins. So what's the probability of the dice being a 6 in the first one? 1/6. And what's the probability of it not being a 6? 5/6. And the same for the second one. 1/6 and 5/6. 1/6 and 5/6. So we can talk about it in combinations of whether there is a 6 or whether there isn't. So we have yes, no, no. We have no, yes, no. No, no, yes. So those are all the options if there's 1/6. So this is looking a little bit less exhaustive. What about where there's 2? So we could have 2 at the beginning. We could have 2 surrounding a center. Or we could have 2 second. And lastly, we could have 3 6s. Like so. So now definitely a finite amount of possibility. And these are all the different scenarios that are possible. Okay, so like getting a 6. And we now also incorporate these probabilities. If we talk about any one of these, let's talk about the first one. It would be a 6 and not a 6 and not a 6. And the word "and" is always associated with the multiplication. A quick side lesson on why. Let's say we wanted 2 things to happen. Firstly, we wanted, I don't know, Ed Sheeran to walk through the door and sing us a song. That's pretty unlikely. But if in the same day we wanted to, I don't know, meet the Queen because she decided to come around, that's going to be even more unlikely. And in the same day we want to win the lottery. Well, that's a lot of things that we want. And the more things we want to happen, like this and that, it's getting more and more unlikely. And each of those are represented by a fraction, call it 1 over n. 1 over m and 1 over o. That's a bad one. Actually, 1 over p. And if we multiply these together, the multiplication of 2 fractions will always produce a number smaller than both of those fractions. So it's very natural to have a multiplication because it reduces the number. For example, a half times an eighth is going to produce a number which is smaller than both of those, 16th. So hopefully, numerically, that helps you understand why we multiply fractions. And we're going to do that here because essentially we want this and this and this to happen. Now let's clear some space. Or maybe we'll go down here. For the first scenario, it's going to be a 6, which is 1/6, multiplied by not getting a 6, multiplied by not getting a 6. In this scenario, we have at least 1/6, and it's going to give us a probability of 6 times 6, 36 times 6, I think is 216. Just double check, yeah. 216. So that's, if you like, up here, our first scenario, 25. I think I keep tapping the mouse, that's what it is. 25 over 216. As you can see, we're going to have a repeated situation on the next one. Because if it's always about whether a 6 is present or not, we're using those same fractions. So these 3 are situations where there's 2 5/6. Essentially, we could represent that as 1/6 times 5/6 squared, and we have 3 of those. Why do we multiply it by 3? Well, multiplying something by 3 is adding it 3 times. And essentially, once we have these three probabilities, we would add them together because each of these represent a win for us. And therefore, we would say we could have this situation, or this situation, or this situation. And whenever you have an or, that's associated with the element plus addition. The reason why is because when we have an or situation, it increases our chance. And by adding fractions together, it increases the probability. So I always like to relate this to the dartboard. So if you're playing darts, and I'll make a very crude dartboard. Oh, that's really more crude than I imagined. There we go. So if you're throwing a dart here, and this is the only sector that you get like a win, that's going to be not the best. But if we colored in this one as well, and this one, and we could now say that we win by hitting it on here, or here, or here. By having more options, we've increased the surface area of success. And so therefore, probability goes up. So we're adding. So using the word or is associated with and. And eventually, if all of them are filled in, it decreases our chance for error being a failure. We can't fail with this dartboard, unless you're counting outside the dartboard, of course. So let's carry on with our little journey. We multiply it by 3 because eventually these three probabilities are going to be added together. They are going to be the same. Okay, so I can write that in just to make it clearer. And so we can multiply that by 3. So here's our first scenario. 25 divided by 216 times 3. Yep. So we're going to keep it in fractions because the decimals get really nasty, but fractions are pretty nice to add together in general. So this is our first 3. Now our next 1, 2, 3 are also going to be very similar because here we have 2 6s. So our next 3 are going to be 3 lots of you see where it's a tick, that's a 6. So essentially we want 1/6 times 1/6, so that's 1/6 squared, multiplied by getting one which is not a 6, that's that one cross. Okay, so the next 3 are, you can see there's always going to be 2 fails in those next 3. Alright, so we calculate that one and we find the probability of those next 3 scenarios. Bear with me. Times 3. Okay, so this one is 5 over 72. Nice. We've got the same denominator. So we've covered those first 6, and the last one is unique again. I promise you I'm not drawing those funny anomalies. It's something to do with the 2 inputs of movement that I have into the device. Okay, the last is going to be where we have 3 6s. That's at least 1/6. Definitely. And it's probably not going to be nice in terms of 72 anyway. 216, right? Because 6 cubed, we did that earlier. So now we've found the probability of all of these. We've added the first 3 and the second 3, and we haven't added the last one. So now we just need to find the probability in total. We add them all together, because it's this or this or this or this or this. 7 different scenarios that we could be winners. So let's go ahead and do that. So we've got 25 plus 5, that's 30 out of 72, plus the 1 over 216. So what would we write here? So at least 1/6. So I'd write that as the probability of at least 1/6 And that's 91 over 216. Great scenario. This is typically a grade 8 sort of question. I think they're grade 9 if you had some algebra in there, but yeah, you used it before the GCSE changed. This was as hard as it gets. This was the A star. It's a good old question. All right, what is this? This is kind of combinatorics. We're looking at the different sample spaces or combinations that could be, and then looking at patterns to see, okay, well, they repeat themselves, so we don't need to know every single one to figure this out. Right, next one. A bag contains 13 purple counters and 12 green ones and 5 yellow. Okay. A counter is taken from the bag at random and then replaced. Alright then, you know what that means? This question just got downgraded. It's no longer one that gives us a little sweat bead. Is that a sweat bead? Actually gives us a different outlook. Is it possible to change a face? Yeah. We have a much different outlook now because this means we're not dealing with conditional probability. After the first picking, it goes back in and probability remains the same on the second pick. These are called independent events. Okay, so what are the events in this tree diagram we have to complete? There's one event, it's the column number 1, and this is column number 2, it's event number 2, it's the second time we pick one. And we have to complete the tree diagram. Love these ones. Typically worth 3 marks if you've got conditional, or 2 marks if you have something like this. So just need to look at the fractions involved. So the probability of purple, we'll call it P, is 13, and we need to know totals. That's 25, 30, 13 out of 30. The probability of green is 12 out of 30, and the probability of yellow is 5 out of 30. All of that all the worded question there is probably a bit harder to read than just writing this out separately, and now a bit more of a clearer head. So we're now going to put it on the diagram. 13 out of 30. Green is 12 out of 30. And we put it on the branch. It could be the other way around. Don't be surprised if they ask you to put the probability here and then y is on the branch. It's not terrible. They can just be, it's essentially this is the journey, right? So it could be anywhere along here that you could see the y and the probability. Now, because all of those stuff, all the counter went back in after that, we actually have the same probability the second time we pick. So let's say the first time we picked out a purple, the next time we pick out a purple, it's the same. And there's still 30 inside that bag or wherever it is we're picking out of. So there you go. Give your brain a rest while I write this. And it is sometimes about patience. We're all doing mathematics every day in our everyday life. And that's less stressful than maths in the classroom. I wonder why. Well, it's something to do with this. Having the patience to write it down. That is maths education. And if you're an engineer, you like the writing less. It doesn't mean you're any less good at the maths, though. All right, a second. Yeah, so let's have a look what the question says. We've completed this tree diagram. And I said I probably want to go through and write the outcomes. PG, parental guidance. PY, I don't know. Prank you. GP, general practitioner. GG, good game. GY, go you. YP, yeah, Upillock, YG, Ugofa, and YY, yeah. And those are our outcomes. We have much more than last time, but this is what we call a 3x3 tree diagram. And you just need to make sure you give yourself enough space at the beginning. See, I've got an angle here which is a lot wider than the angle of the second branch set. Helps a lot. I'm not going to go through and work out all the probabilities because, as I said earlier, that's okay if there's not that many. This time there's many. But I will do the first one to demonstrate le méthode. Something like this. So 13 squared is 169 and 900. Okay, so there's just one example of what we might want to do. Let's see if we need to. What's the probability that the second counter is purple? Okay, so in this case we need to highlight all of the questions that are going to be working for us. I'm going to do that as such by circling these, and then I can rub it out for the following questions. You need to find a method that works for you when it comes to not being able to rub it out digitally. So if the second one's purple, definitely true there, and here, and here. So we've got 3 to work out. Okay, great, we've worked one out already. Follow the branches along. So this one's 12 over 30 multiplied by 13 over 30. And 12 times 13, 156 over 900. Do you ever go back to your work and wonder what you wrote? Just take your time, and it's worth it. 5 over 30 times 13 over 30. 50 plus 15, 65. Alright, so we haven't done them all yet. I'm not discounting the fact that we might have to go on and do some more, but the probability that the second counter is purple comes from this at the top here, or this in the middle here, or this at the bottom. And when we can have multiple options for winning, we add them together. They all have the same denominator, so my sum is 169 plus 156 plus 65, which is 390, with a denominator of 900. So the probability that the second is purple, 390 over 900. Now I'm fairly certain that this is going to cancel. I can see straight away we've got the zeros, and then we've got a divide by 3, which is 13. I think that might be it, but you can put it on a calculator just to double check, and it'll automatically whittle it down, and that's correct. 13 over 30. Hello, button. Let me move that. Okay, find the probability that both counters are yellow. Well, that's nice. We haven't done it, but it's pretty straightforward. There's only one situation where it's yeah, and that was yeah. So in this case, we've traced it across again. 5 over 30 times 5 over 30. Lovely. 25 over 900. And job is good. So probability of y. Yeah, 25 over 900. I'm pretty sure that that cancels down as well. We'll divide by 5. So 20, okay, so 36. That looks more like a 3, right? Okay. Double checking. Yeah, we're good. Okay. Last one. Find the probability that the two counters selected are different colors. Probability different. Lovely. And it's just the same as before. We're going to go through and figure out all the ones where they're different. So that discounts PP, GG, and YY. So we've got some calculating to do. Let's circle them first. We've got PG, PY, GP, GY, YP, and YG. Yep, happy with that. So calculation time is here. Unfortunately, there's nothing clever about what we're about to do. We have some of the information, we don't have some others. It's not like we could figure out one and then take it away from one. So just the hard slog of patience, and bear with me and have a go. Again, if we're going across the tree diagram, a good rule is that across is across, means multiply. And when we're going down at the end, we're adding. Could be a good one to remember if you're like, oh, am I doing the right thing? It's quite reassuring to know these little things. Let's get rid of that. Uh, 50, done this already, 65 over 900. I'm going to need another drink. If you have any questions, please ask. I know I have not seen the exam that just happened. Quite rightly, it's kept under lock and key and hopefully used as a mock exam some other time, but I'm sure there's somewhere online where they're talking about the questions that people remember, because photographic memories are a thing. I, for sure, if I ever had time in the exam, I would write down every question that was easy to write, apart from all the ones with a load of words. And I would, for the most part, be able to piece together how I did in the minutes afterwards. And that brought me some sort of certainty before the exam period was over. But each to their own. All right, well, I think we're done. So we just need to add up the relevant ones now. So 156 plus 65 plus 156. Yep, plus 60 plus 65 plus 60. That's it, 6 numbers. 564. Is that what you got? And that's all over the same denominator. I'm pretty sure that cancels down. For sure it's an even number. And quite rightly it does. Doesn't say to give it in the final form as a cancel down, but if you want to be super duper extra good to yourself, don't worry about the exam. You're going to keep the highest of standards there. Right, I'll let you think about that one for a second. I'll show you the answers if you want to double check what you're doing, and I'm going to do up the buttons on my cuff. So I think they're rattling in the background of the video. Alright, that should solve it. Yay, tree diagrams. See, what we lose in the fact that it's complicated, because it's not, it's a basic independent event tree diagram. We make up for in the fact that they ask us loads of questions and there's a lot of addition going on. So good job. And again, if you have any questions, leave them in the comments below, or you can write in the comments now if you're here. Look at this greatness. I love doing these. These are one of my favorite things to do. And we're going to do it with the mighty fine tally method, which I've developed. I'm unaware of anyone else using it, but it's fine. It works. We can exploit it if no one else is. Right, let's go for a red and maybe a bit more color. Okay. So how does this work? Sometimes these can be quite complicated, right? So we're talking about not A in union with not B. So let's assume that some people don't even know what these symbols are, right? This means union, which is nice because it begins with a U and it looks like a U. And the opposite way around, upside down, This means intersection. Okay, so that's what we're based on. A union is A or B or both. That's literally a definition if you want. A or B, I'm going to write it as nice as I can, or both. Now we'll talk about what that looks like a bit later maybe. Intersection is just A and B. Okay. Let's have a look at the question, and I'll introduce you to the tally method. So to do this method, to figure out what section they're talking about, if we're talking about a basic section, and if I have a basic section here, let's use B to begin with so you can see this. Blue. So section A would be this here. Okay, so this circle on the left hand side, which is labeled A, is the probability of A. And if we talk about B, it would be this circle on the right. And if we talk about the intersection where they cross over, this here in the middle is the intersection. So that would be written as A and B. And it's probably a good time to talk about that. This here is pronounced as N. And this would just be called union. You may hear N in a minute. That's what I mean. So if this in this here, like I'll just color again, is A, then if we look at this symbol, which is a hyphen, this little thing at the end here, this means not A. So we'll get that written down so we can not A. So we know what A is. It's that circle. So not A is everything outside that circle. Now we don't need the tally method for this because this is pretty straightforward. I think I've got the highlighter on something too big. But there you go. That's good enough for this one. I'm going to make it a wee bit smaller. Okay, so that's not A. So everything that is not A. We could do the same down here with not B. So B is in this circle here, and not B would be everything which is outside of that circle. That includes the outside area. And it's a bit more precise, but a bit slower to color these in. Okay, so we get the idea of the basic thing that we're doing. We're coloring in the relevant section. And now they get a bit complicated, you see? So let's start with the next most interesting one, which is this one. This is the pure definition of the intersection. An intersection is where they both occur. And to use the tally method, we'll start by defining all of the sections that are A. A is this and this. Those are the two sections that if you colored them in, they would be A. Next, we're going to look at the sections that would be B. That would be this section and this section. The intersection is the bit where they both cross over. So, can you see how the tally helps? The tally is where it has occurred twice. That's this bit in the center. And what we have just colored in is the intersection. We've colored in the answer. So that's exactly what they're after. This means intersection of A and B. I think that's all we can say about that. And the next interesting one is down here at J. This, as you can see, is the strict union between the two. Before we move on, let's just make a note of what we did for the intersection. We colored in the section that occurred the most. So for union, we're going to shade the highest frequency. Now I'm going to just, there's a wee bit of a delay on the screen, so I'm going to go a bit slower, but that will mean you can actually read it. And with intersection, oh wait, hold on. The highest frequency, no, that was intersection, we've already done intersection. It was the union that we're about to do. So for the union, we're just going to shade all sections that have a frequency. Or let's say all sections with a tally. And we'll see why now. The union is defined as A or B or both. So if we come down to here, A, let's do tally. A is here and B is here. And so if we were to colour in all the sections that have a tally, it would be this here. This part represents A. This part represents B, just B. And this bit represents both. So what have we coloured in? We've coloured in the two circles. There's no overlap involved. It's just, I know there's two tallies in the middle there, but essentially they just serve to count that section once. And it's actually really important when you get to A level and beyond that we know that if I took a circle A and let's say it had this particular area and this B, and then we were to overlap them like this, there would be a section there that is counted twice. Like, what have we coloured in? We've coloured in two circles, but we only wanted to colour in, let's just draw the circle at the side there. We only wanted to colour in this amount. Because that was there, we coloured it in twice. That's not what we're getting at. So if we want a strict definition of the union, it's going to be the area or the probability of A plus the area or probability of B, but we have to take away that middle crossover. And how do we write that? That's the intersection of A and B. So there's a definition, actually, that we can stick to. It's a little bit of an extension. You don't need to know it at GCSE, but like I thought it was appropriate to just look at that there to define it. But I appreciate that might be not for everyone, so I will rub it out for the purpose of this worksheet, which you can find the answers on Patreon afterwards. But the union is A or B or both. So if you hear that sort of language, you know what you're going for. And it looks like this. But easier, just do the tally method and colour every section that had a tally in. And then you'll find quite easily what the section is that they're talking about. Alright, basics are out the way. Now we're going to go through and do some of the more hard ones, the weird ones. And we'll hopefully work our way up into order of difficulty. Let's look at F. A and B, but all of that has a little hyphen outside. Do you remember what that means? It means not. So whatever A and B is not that. So I'll just remind you, A and B is in the middle there. So it's everything which is not that middle bit. And, you know, colouring can be very therapeutic, so probably should enjoy this and not want to rush through it. Okay, so that's that one. Is it what you thought it was? In the same of this, the A union B with a not. So A union B was this whole centre circle area, right, even the middle bit. And not would be everything that isn't. So we're talking around the outside. Oh no. the anomaly occurred. I think my hand's too close to the mouse. Let me move it. My live streams get haunted by the anomaly. It's a thing. Okay, cool. So now that's pretty much the easiest, and all the rest of them require the strict methodology, I would say. So let's use a different color because they're a bit harder. I can distinguish them. Looking at question A, why not? So we first of all define the first element, which is not A. So if these two bits are A, not A is this section and the outside section. So that's that done. And now not B, you could look at what B is, and then not B is outside of that. So it's this section, and again, the outside section. And I'm going to put the tally next to that, just easier to see. Okay, we've done the elements in tally. And in between those two elements is a union, which, as we saw up here, union means we color in the sections that have a tally. So let's do that with orange. So it's this section for sure, and the outside section. So I keep my pen down there and travel over. It's this section here as well. So actually we've already drawn this. It was A and B with a hyphen on the outside. Just see, I'll have a look at that over there. There's F. F has produced exactly the same shading. So I think we can be assured that there's more than one way to write each of these sections. That can either be scary or reassuring. But if you're confident in your method, you most likely might be right. So, oh, did I rub that out? Let's add the O on union. There we go. On to the next one. Absolutely love this. It's such fun. Right, let's have a look at G. So we've done not A before. We can get that one really quick. We've done not B before. But this time, we're looking at the intersection of both of those. Intersection, just to remind you, we shade the highest frequency. As you can see, that's the outside. That's got 2. The others have only got 1. We don't shade in any that doesn't have anything in it. So for sure, that's not even going to get touched. And there we go. What is this the same as? This is the same as union of A and B, but the complement of that. And actually that's a nicer way of thinking about it, because it doesn't always work in a language to say the not. So here's A and here's not A, but it's also known as the complement of A. That actually rolls off the tongue a wee bit better. Okay, let's look at the next not A. We got that one here and here. This time it's B though, so that's this section and this section. And the union tells us that we're going to be shading in everything that has a tally. So it's this section and this section plus the outside. Now I don't know any other one that we've done so far that produces this, but I like to call this the crescent moon shape. Yeah, on that right hand side. And if we make a prediction, this question has a complement of A. This one has a complement of B. What do you think it's going to look like? Place your bets. Here's A. Here's not B. And we'll shade it in and see if you were correct. The union means that we're going to be shading in all of those with a tally. So it's those two and the outside. Yep, hopefully you predicted. It's just the flipped around version of that previous one. The crescent moon is on the right this time. Okay, 2 more to go. Such fun. With K, we're doing not A. We got it. And we're doing B. But this time, it's an intersection. Intersection means we just colour in the section with the highest frequency, which is this here, because essentially they overlap here. Those 2 sections have occurred twice in that region, so they overlap. And the intersection refers to the overlap. That's what we want. This is the crescent moon in a different way. It's highlighted this time instead of missing. And finally, you can make your own prediction about what's going to happen here, looking at the question, but this time the complement of B. But we don't always do assumptions. We probably want to work it out properly and prove what we're thinking. So A is this section and this section. And not B is everything outside of B, which is here and here. And we were proved right. It's the opposite crescent moon. And that's a really good exercise for getting to grips with set notation when you're having to deal with Venn diagrams. Super useful. Okay, as I said, this will be available, the answers, on Patreon if you want to go there after this. And you can grab them. Okay, number 7. Jacob. Who's Jacob? Alright, let's make it a bit zoomed out. Couple of questions. Here we go. Jacob loves to have a tea and a scone at a local cafe. Who doesn't? Right. Whilst there, he reads Informed magazine with a probability of 0.6. Jacob is not in control. He's a random reader. And Big City Life magazine with a probability of 0.4. No comment. The probability that he reads either one of both magazines is 0.7. Find the probability that he reads both. I think that's meant to read either one or both. Not gonna lie. I'm gonna have to change that. Because if it didn't, then essentially the question is already answered. So let's start that again. All right, so the way I see this is Jacob is in a scenario with himself, and there are 2 options. This calls for a Venn diagram, just like what we've been doing. You don't have to do it with the Venn diagram, not at all. Me personally, I like Venn diagrams. If the scenario fits, I prefer visual. Now, we do have 2. It's possible that he reads both. Could totally take both, put them in front of him. So 2 circles. There's no reason why you couldn't have both at this cafe. My circles are getting bigger and bigger. This is so dumb. Hey, what am I even doing? Right, Samsung have this. This is an old model of it. It's so much better on the tablets. But on the PC, you can press the button and say, recognize my stuff. And it turns it into these nice geometrical forms. Now it's far greater if I copy paste this. If I do select. There we go. Can't ask for better, can we? Venn diagram. So one of these circles has to be represented by something. So we'll call Informed magazine I. And I hope I don't regret that. And Big City Life is B. No reason why or why not. So I on the left and B on the right. the probability of 0.6. So informed magazine is 0.6. It means that the total of this circle is 0.6. So if I coloured that circle in with its two sections, it would be 0.6. But I can't tell you right now, like, how much is in each section. We'll hopefully figure that out. And the probability of Big City Life magazine is 0.4. So let's do that on the top. This whole circle will eventually add up to 0.4. So this stuff in the middle has to be fairly small, because there's not much to give for the 0.4, but we'll see. We'll see. This is the giveaway, I suppose. The probability that he reads either one or both of the magazines. So that's A or B or both. Okay, that's essentially what we saw previously, and I'll remind you, look, the union is A or B or both. Let's have a look at what the union was, if we remember. Where is it? Down here, J. Okay, that was the union. It was the three together in the center. So essentially, all of that center adds up to 0.7. Golly, do I have space? No. I'm going to write it here. So all of that is 0.7. Okay, do we have some logic here? I think so. We've got a couple of things. First of all, if all of those circles are 0.7, outside of them are 0.3. And if both of them, like those three sections, 1, 2, 3, add up to 0.7, and these two here, 1, 2, add up to 0.4, this must be 0.3. And likely the other way around, if these two sections add up to 0.6 and they all three add up to 0.7, then we're missing 0.1 on this outside. But we know they all add up to 0.7, so we're missing 0.3 in the middle. And we'll double check that works. 0.3 and 0.3 is 0.6. 0.3 and 4 is 0.4. It should work. It's all based on the same logic. And then they all add up to 1. That's amazing. You can draw a Venn diagram to help you in this scenario. In fact, should I keep them? I just thought it was getting cluttered. I'll keep them. You can draw a Venn diagram to help you in this scenario. You don't have to, but I always do. So find the probability that he reads both magazines. It's not in the question, but it is here. So what we're looking for is the probability of I intersection B. That's where they both get read. That's 0.3. You can clearly see that from the Venn diagram. It's that section in the middle there. That middle section essentially means both. Sometimes the question will say by drawing a Venn diagram, but it's not always necessary. And informed magazine only. So if you want to like go through and try and figure it out by all these logics and probabilities in your head, it's pretty hard. I think the Venn diagram shows quite clearly what section is informed only. So this is both. Well, that's a mixture of both. This is here a section which only includes the B. What was B again? Big City Life. And this section here is the section which is only I. Doesn't include B, it's just I. And so that's informed magazine only. So all we do is read the probability that's in that section, and we found our answer. So it can be useful that way. You couldn't have found 0.3 from the original question. So whether you do it with a diagram or not, you had to do something. The question, I suppose, is how do you define that little moon? And now we had a couple of different options back here, didn't we? Is this here? It's A with not the other. So when you get good, you start to see these things. You see You see this here. This is A. And you want it to intersect at this point only, because this is the bit we're interested in. It's pretty straightforward to see that everything outside of B would intersect with this part. So we could call it not B. That's one way of writing it. So we could say probability of I intersection with not B is equal to 0.3. Now that's one way of going backwards. So sort of throw that in there as an interesting exercise. You can find sections and define them with set notation, but we probably just want to say this would be fine too. Like, you didn't have to go really fancy. This is probably the best actually, because you've got the scenario involved and it's pretty clear. But I wanted to take the opportunity to say you can look at a section and then use set notation to define it. And remember, there's so many ways of doing it. There's only one way. Okay, so that's a nice roundup of various probability questions. Some of it quite advanced, some of it standard stuff, but still good practice. This one probably one of the harder questions, number 3, and this one, number 2, because it's conditional probability. So watch out for those in the exam. The other type, which is not on here, but it's in another live stream that I've done, and I'll link it in a comment down below, is linked to something called Hannah's Sweets. So you may, let me go to the end of this. You may have seen this really difficult one called Hannah's Sweets question. And I made my own version of it, like not the same, but like in a sense you had to use algebra. So it told you that there was X amount of sweets or something. So that all of your tree diagrams looked like this, where you had like an X on it. Well, eventually, once you worked it through and did all your multiplication, you ended up with, I don't remember exactly what it was, let's just call it this, a quadratic equation to solve in order to find out the value of X. And people were stumped because it looked like it was going to be this really nice like tree diagram question like this, where it was like, oh, I know how to do this. I can just draw these branches. I can put the numbers. I can churn through the numbers, and I'm really happy because I know what to expect. But part A said, prove this. And they thought, okay, well, I thought it was a probability question, and maybe it isn't. And people gave up, started crying. And so actually, you shouldn't get worried. When it says prove, you shouldn't always focus on this. You should focus on some of the key parts of the question, which would probably look like this in question 4, and think, well, what can I do? And just go through that process. Like, if imagine this 12 wasn't a 12, instead it was X. You could still do this whole process, but it would be in terms of X. So whenever you see a 12, it would be X. And then at the end of here, it wouldn't be 12 over 30, it would be X over 30. And then it wouldn't be 156, it would be 13X. Don't do this. 13X over 900, right? So you can still do the process. It's actually, actually would be easier to undo that. I don't want that in there. No, but anyway, my point is you can still do the process. And you need to be confident that it's going to remain the same process, but just with a letter instead. Okay, I think I've undone everything now. And once you get to the end, you're going to be adding up, but you just need some algebra skills. And what they found, if they just ignored this initial blocker that made people shrivel, if you just carried on, you ended up getting this without much effort. It's like you're just doing what you normally do. So that's what the exam does to you. You experienced it already with paper 1. This is your exam. It's totally unseen, and you get this one shot at it. It's like jumping in cold water. So you need to be preparing yourself mentally for that, to believe in yourself and say, you know, I've got this. I do know a lot more than I think, and I'm going to stay calm and rational, and that's 60% of your battle. And you see stuff like this, it's not going to be beyond what you already know. Figure out the topic. It was probably probability. Do the process and stay calm, even if there's algebra involved, because they're trying to shove algebra in everything now. So just remember what the ordinary process was, and you'll be fine. That brings us to the end. I will link the question like that. I'll find it somewhere. I know I can't quite think where I put it, but it's a pretty good rival to Hannah's Sweets if you want a couple of questions like that. And that's it for this time. Probability over. If you have any questions, you've got a few seconds to ask them. If not, great to see you around. I'll hang on for a couple of minutes to give you time to type. So whilst you type, I'll just go down memory lane and look at the questions we did here today. Ah, yes, this one. Very good. Yeah. Loved this one. Yes. Really simplified it when we looked at bins. Lovely. I love seeing those patterns, you know, it simplifies it down and you feel like you've got just such a handle on it. This one was cool. I really like, you've got to appreciate things that make you think a bit, right? Keep you on your toes. So you really do have to double check everything, and this is a great question for that. I'm very grateful for these tough questions. Sometimes we have to make assumptions so we can stay calm and we can think rationally and make those assumptions, because maths is not always going to correlate very well with real life. It just doesn't. The only glue that holds real life to maths is the assumptions we make. There's all sorts that can go wrong in real life. Numbers do not lead to exact eventualities. Not always. Not always. More often than not, they don't. But depending on the resolution we choose to live life at, they're good enough. They can be good enough. And that's why we have physicists. You know who you are out there. You accurate people who like to relate maths to a little bit more grounding in the real world. All right. Thanks for helping us understand. No problem. Wish I could say a name without worrying how to pronounce it. Is it Ray? It's absolutely no problem. Coming to the end of our journey this year. And what a year it's been. Every year I always say, it's going to go so fast. It goes even faster than I imagine. And but it's glorious. You know, it's your life. It's a year in your life, and you look back and it'll be lovely golden days. Okay, so you go to that exam and you grab it. Best of luck. Good night, good morning, wherever you are.